This is the pre-lecture video for chapter 24, lecture 1. In this video, I'll be talking about catalytic carbon-carbon bond forming reactions. So throughout the semester, we've learned a variety of carbon-carbon bond forming reactions. And these reactions are incredibly powerful and important for the synthesis of complex molecules such as pharmaceutical drugs, complex molecules such as polymers. And you'll note that many of the carbon-carbon bond forming reactions we've learned only occur with certain functional groups or certain relationships to functional groups. For example, carbonyl additions, well, they require a carbonyl. And this is great if we want to form an alcohol eventually. Or conjugate additions, we know how to form CC bonds, beta to carbonyls or beta to pi accepting groups. Again, this is great if you want to form a CC bond beta to that. Or a Diels-Alder reaction. This is great if you want to form cyclic rings. We've learned many others, and they're summarized on page 1096. But suffice it to say that carbon-carbon bond forming reactions are important in the development of chemicals we need in our day-to-day life. An extremely powerful strategy that has developed over the past 30 years, past 40 years, has been the use of transition metals to help mediate these bonds. In fact, we've already learned one such reaction, a Gilman reaction, where we take a diorganocuprate. Copper is a transition metal highlighted in green here. And we take this diorganocuprate and we react it with an organohalogen species, abbreviated as Rx in red. And what this reaction does is it forms a CC bond between the organocuprate nucleophile and the organohalogen electrophile. And this is just one example of a CC coupling reaction mediated by a transition metal. One thing we didn't really talk about in this reaction is what the copper-containing product is. And formally speaking, immediately after the reaction, we actually just get a mono-organocuprate. Now, like many things in organic chemistry, reality is a lot more complicated than this. But one thing you may wonder is, well, why can't we reuse that copper? We know how to synthesize Gilmans, and we can take a copper species and treat it with an organolithium, and we could regenerate it. We could take the product of our reaction, and in theory, we could add organolithium and regenerate it. And in fact, our copper could go around in circles and take in substrates, our X and our lithium, and it could spit out products where R is coupled to the other R group. Now, why couldn't this sort of, this cyclic pattern occur with the copper so that way we could use less copper? Well, in this specific reaction, that doesn't work that well. However, there are examples where this is the case, where we can have one reagent accelerate the rate of reaction. That is, if we take Rx and RLi and we mix them together, they react very slowly or not at all. So the copper in this case is what's called a catalyst. A catalyst accelerates a chemical reaction or makes a reaction that doesn't actually occur, but is also regenerated in the reaction. A Gilman reagent, due to sort of practical limitations, is not really a catalyst. But we are going to spend the rest of this video talking about examples where that's the case. And this is an introduction to what's called transition metal catalysis, specifically in the context of CC coupling, an incredibly important synthetic transformation. So what might that look like? Well, we could have some sort of metal, and it could interact with some sort of Rx, an electrophile perhaps, and form bonds to it. We've already learned this sort of reaction. If you imagine metal is magnesium, we've learned that magnesium can insert into carbon-bromine bonds to make a Grignard reagent. Now, what if that metal could undergo a second reaction where we stick another group to it, and then that metal could do a bond-forming reaction like the Gilman reagent does to form a CC bond between those. Okay. And this is what we're going to be talking about. And most of the reactions in this chapter would never occur without the help of the metal catalyst. So we're going to talk about the mechanisms of these reactions, prominent examples of these reactions, as well as why they are so powerful in their synthetic scope. That is, what sort of molecules we can make with them. So the advantages of these processes are that catalytic CC bond formations, these transition metals facilitate reactions that are otherwise impossible. I already said this a couple times, or are very difficult. So sometimes these reactions are the only way we can make a certain type of bond. When a metal is able to do, or when a reaction is able to use one reagent many times over in sort of a cycle, this catalytic cycle we talk about, this reduces the number of quantity of reagents, solvents, and purifications. This is a waste reduction. Catalysis results in waste reduction in most cases. And this is important because chemical waste can be, for an industrial process, can be dramatically reduced. So intentionally designing a chemical procedure or process to decrease toxic waste byproducts is a whole chemical field in and of itself called green chemistry. We've been talking about this, all right? We've been talking about the principles of green chemistry in class. And so these reactions are not only synthetically powerful, but they're also addressing one of the historic limitations of chemistry in general, and that is these wasteful process that generates toxic and difficult to dispose of compounds. So what are the reactions we're actually going to learn? What are some examples of these? Well, we're going to learn 4 major classes of reactions. And many of these have actually won Nobel Prizes for how much they've transformed organic chemistry. So one prominent example, it's sort of a general class of reaction called cross-coupling, are the Suzuki, Stille, and Negishi couplings. These reactions often form CsP2 carbon-carbon bonds. They're limited to that, but that is sort of how they developed and what the Nobel Prize was awarded for. These reactions occur with catalytic palladium, and they have well-defined nucleophiles and electrophiles in the reactions. I have the nucleophiles highlighted in blue, and I have the electrophiles highlighted in red. And you can think about this for a second, and I would encourage you to do so. How would you make this bond highlighted in blue here? How would you make this bond through other reactions we've learned in this class? How would you stitch these 2 aromatic molecules together? We, in fact, haven't really learned any ways of doing this. You might think of some way you could do a complicated Diels-Alder and then oxidation chemistries to get rid of CH bonds. But these reactions are powerful for their ability to create bonds we really don't have good alternatives for. Another closely related reaction that we'll be studying is called the Sonogashira coupling. In this reaction, we take, again, an aryl electrophile, highlighted in red here, with an alkyne. This allows us to form alkynyl aryl bonds using palladium and copper catalysis. So this would be better depicted as palladium plus copper. Oops. And so Sonogashira reactions are the reactions between a terminal alkyne. What do I mean by terminal? It means it's at the end of a molecule, so it has a CH bond. Terminal alkynes and aryl electrophiles. So the alkyne ultimately becomes the nucleophile, and the palladium and copper work together to form the CC bond highlighted in blue. Again, this is an incredibly difficult transformation to think about for other reactions we've learned. We'll also be talking about what are called Heck reactions. These are the addition of an aryl group to an alkene to form a new compound. This typically occurs under palladium catalysis, and again, uses aryl electrophiles. In this case, the alkene can be thought of as the nucleophile. Then finally, a reaction that breaks the trend of nucleophile and electrophiles is called alkene metathesis. This is where we take 2 alkenes and sort of stitch them together, and we give off an alkene product here. This alkene product is just ethylene. And this reaction was awarded to 2 research groups in 2004. This Nobel Prize, sorry. Nobel Prize for this was awarded for this reaction in 2004 to 2 groups that developed this reaction because it's really that important. And again, you can think about how we might form this CC double bond. Well, we might use wasteful reagents like Wittig reagents. Remember that? We could take a phosphorus ylide and a aldehyde and couple them together. But we talked about in one of the green chemistry lectures how this is incredibly wasteful. And so you need to know these reactions. You need to know what suitable reagents are for them. In this case, most of the other reactions require aryl halides or pseudo halides. We'll talk about what that is in lecture. You need to know what type of catalyst mediates or what type of metals catalyze these transformations. And finally, you need to be able to use these reactions to synthesize a molecule. That is, you need to know how to, what to mix together to get the product you want. And we'll be talking about the mechanisms of these reactions in class. These are the 4 transition metals catalyzed CC reactions that we're going to use to describe the greater field of transition metal catalysis.